I'm Konstantinos Mouzakitis, or Mouza, that's what everybody calls me. And I'm a principal solution architect at NScale. So I deal with all the things technical, with all the large projects that we're deploying right now, gathering all the requirements from customers and liaising with the technical teams in the backend just to align all these for technical deployment of the projects. NScale is a hyperscaler for AI. We own the full vertical stacks. We own a lot of data centers. We partner with many others. We deploy and own the infrastructure as well as the cloud stack on top. So we try to give AI services to our customers with HPC and high performance essentially is every time on our mind. So we design all the clusters with absolute performance in mind. So far, it's mainly large enterprises that we work with, as well as hyperscalers. So we deploy large GPU clusters for them. I started off I think it was 12, 13 years ago as an HPC engineer, designing high-performance computers and clusters for traditional HPC workloads. But things are progressing, evolving. So AI has become a huge area right now. I see AI still as as an HPC use case, if you'd like. I see a lot of shared requirements essentially, if you'd like, between the two workloads, you still need a fast backend storage, for example, or backend networking. Most of the AI workloads right now, whether it's training, fine tuning, or even inferencing on distributed inferencing, they need a fast, very fast network in the backend. High throughput, low latency. So in that sense, it's very similar to HPC. But also, it's quite different as well, specifically on the software side of things. When you have FP64 on the HPC side of things, but in the AI you don't need that high precision, so you can work with FP4, FP8, and all the vendors, they have been designing accelerators and chips according to that. So you see specific hardware for HPC. Specific network topologies. We design everything on rail optimized topologies and everything, for example. So some similarities, some differences. We started off as large training clusters for everyone, just because there was a need of those large models back then, but now it's mainly inferencing. And not just traditional inferencing, which you can potentially do in one or two nodes, but distributed inferencing. So we see the need of 10,000 GPU clusters running a single inferencing job, for example. So it has evolved, and I think we'll at some point, once we have all these large models as well, we will go back to some fine tuning of those models, just because they're trained to be generic. But there will be companies and enterprises that will need some more specific models for their use cases, so they will need to fine-tune them. That's one of the conversations that we're having with the customers, right, early on, just to understand the requirements and design the clusters on top of those. But even with inferencing versus training, for example, as I mentioned, we do see similarities in those workloads right now, because inferencing becomes distributed. So you still need the large cluster that you would typically use just for training to put your inferencing workloads on them. So, and at NScale, we design, as I mentioned, all the layers of the stack. So we have the orchestration layers to run not just, inferencing jobs, but training and fine tuning as well. I think it's a couple of things. First of all, it's the flexibility to be able to host, multiple use cases and multiple different workloads, as I mentioned, training, inferencing, fine tuning. It's also the automation that you need to provide. No one wants to go and manually create their own virtual networks and clusters and everything. So we have the abstraction layer to create all those automatically. And then, even if you go further up, some serverless inferencing and serverless fine tuning as well. So people just want to jump online, not even care about where their workload runs underneath. They go online, they put a credit card in, for example, and they pay for some serverless inferencing by the token. So it's that flexibility and the amount of layers that you need to have on your stack to be able to not only provision, infrastructure as a service, which is, a bare metal GPU server, and you go and do whatever you want with it, but also the platforms on top that will provide the automation for your workloads as well. There are people, that do want like a per token, because it's easy. You go online, there are some models on there. You're inferencing for an hour or two, and it's an on-demand model essentially. But you will have those are the customers that have smaller requirements, right? Sure. That they need the on-demand capacity for a couple of hours, and that's it. Then you have on the other side the other customers that want those large supercomputing, the thousands of GPUs in a single cluster, and that's a different story completely. And even between those, we have customers that want pure bare metal. They go and deal with the software layer themselves. But we also have other customers that want to tap into our platform stack and APIs and everything. You have to be, of course, competitive in the market and everything, depending on the models, because each model has a different pricing per token, for example, depending on how big it is, how many resources it consumes just to inferencing on that model. So it's a complex equation. On the customer side, I think it's mainly the automation of everything, of the automation of the workloads, and also just to be able to because we have customers that have needs not just in one data center in one location, but multiple locations. So trying to tie all these locations to be treated as one cluster, for example, and especially with the data that needs to be moved between those locations in the backend, that is a challenge. And that is something, for example, that we're working with Vast on, and all these cloud native features that Vast provides, like global namespaces, in fact, enables us to provide those services to the customers a bit more, efficiently and cloud natively. We're deploying hundreds of thousands of GPUs, and from the hardware side, that's the main thing. And of course, all the cooling capabilities. So designing the data centers just to feed all that, and we know that the chip technology that doesn't hold back. So we have new products every 6 months, almost like every year. So the next iteration of GPUs are going to be more power hungry, more dense. So you will need to adapt to all that on the hardware side of things, and on the software side, it's us developing capabilities to be able to automatically move the workloads to where the data is. So that'll be a huge thing. As I mentioned before, data movement between sites is not cost efficient, so it's better to move your workload to the data instead of the other way around. Well, of course, sustainability is one thing, right? And we try to be, sustainable in all our data centers. On the software side of things, what, again, we could do is start distributing not just, the hardware, but the software, as I mentioned before as well. So we can go closer to the edge with smaller deployments instead of, needing to have a data center with 200 megawatts of capacity. You can have a modular, container type of deployment next to your customers' facilities, for example. So right at the edge, And that will distribute the power a little bit more evenly around the globe, essentially, right? Instead of having it consolidated into the data centers, you send it to the edge. So there's always going to be challenges. You can bring your data, again, with your cluster at the edge at a smaller capacity and have a larger consolidated cluster back in your data center. So that there will always be need, for a larger cluster in the backend. But if most of the inferencing, workloads run at the edge, I think that's a good way to distribute the energy and minimize the footprint. I mean, we're exploring new technologies, new liquid cooling, different liquid cooling solutions. Supply chain, for example, is a real pain sometimes. So we're trying to be proactive, get everything as soon as we can. Through our partnerships with all the major accelerator manufacturers, we can have early access to the new architectures as well, plan for those. It's not just, deploying the model. It's actually now you need to have positions like, prompt engineers and everything just to make the model inference your workloads and everything as efficiently as you can, right? You need the output of the model to be tailored to what you specifically asked for it. So prompt engineering and everything. So AI engineers, logically, and so on the software side as well. So there are so many different deployment mechanisms for all these inferencing models. So yeah, it's a vast ecosystem. Well, apart from the all the extra hardware you need to have, of course, for the model, because you need, of course, the GPUs and everything to efficiently run it. It's not just a web application that it's like a living thing, right? So you need to interact with it. You need to prompt efficiently just to get the results you need. So you need to adjust it to your use case. So yeah, it's a bit more complex to deploy and maintain as well. We are in a hiring spree right now, and we see good AI engineering. It's a bit hard to find. It's all these big companies, of course, that try to get the talent early. Scale is one thing that AI needs, right? So we're talking again about thousands of GPUs and everything. So the products that can actually provide services at that scale, that I think they're the ones that are doing great in the industry. That's one of the main criteria for us as well when we try to assess a new product, test it, maybe integrate it in our stack. It needs to perform well at scale. So yeah, I think that will need loads and loads of capabilities at the edge. Like for physical AI, you will need a small supercomputer next to where you're running all that physical AI, right? So it's not that agentic was the previous generation of AI, if you'd like. As Jensen said, physical AI is the next one. So you'll definitely need more capability at the edge, just because you'll need that power to run all these robots and whatever. We provide the sovereignty because we give them like sole access to a data cluster. We have clusters specifically for some customers, so it's only their data essentially running on our cluster and on the data on the storage infrastructure in the backend. So we are a UK-based company. I do see some requirements for sovereignty, especially in Europe. In Europe, we do see its power is a little bit more scarcer than it is here, but at the same time, we're working, for example, at the Nordics, and over there, power is cheap as well, right? It's easier cooling as well, pretty much cold all year round. So there are the advantages and disadvantages between Europe and here, and we're also looking now at APAC as well, expansion and creating some data centers there as well. Cooling is a huge thing, right? So we're looking at we're moving into an era that air cooling your GPUs won't be possible anymore. You'll need liquid cooling infrastructures. You need smart ways to create your DC so that it can accommodate that. We working with a data center in Portugal as well. It's not your typical cold country to deploy a data center on, but because the data center is next to the sea, for example, they're able to utilize that, like they're getting the seawater and using that to cool their equipment. So yeah, liquid cooling, 100%. There are loads of interesting solutions out there, and it's gonna be the only possible way to cool the GPUs in the future. It's helpful, but it needs some governance and high level checking everything as well. So it's very helpful. It can help you during your internal developments and everything, the tools that you can use as a company to automate some of your processes as well. And I'm not just talking about deploying the software, but internal IT company processes. So they are helpful on that side. We also need someone to double check everything, at least at this point still. So the models are becoming stronger and stronger though. So at some point, junior developer positions and everything might be taken over by some of those models. But you'll still need, some experienced programmers and everything just to double check and collate everything and make everything work as a whole.